Hello and welcome back to a new video here on the Ludwig Fusel channel. In the last video we talked about a few helper functions that help us manage our memory. Today we're gonna continue on expanding our knowledge by introducing a few modifiers for variables. Before we can get started, we first need to construct ourselves again a problem so that we can solve it with the new features. Well, I'm gonna give you a problem. It's already constructed there, but you never really saw the issue there. You can see that we had a bit of code duplication regarding the size of the array. So you basically can see that the array was basically defined here as a size of 32 bytes, and we always use it. So we have written 32 here, 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 and here. So 1, 2, 3, 4, 5, 6, 7 times. So 7 times we have written the same piece of code. And that's not something that we want to do. So let's maybe try to fix this. So how could we store this? Well, we could use a variable and call it like element count or just count to make it a bit simpler. 32. Alright, so if we would now try to replace this, we can try and do this, and we're gonna see that it works sometimes and it doesn't work the other times. So first of all, doing it like that, you can see it works, but it doesn't work on the array A and array B here. What is the issue that it doesn't work on the arrays? Well, it is a variable, which means that it is done dynamically at runtime, or that the variable can change dynamically at runtime. However, as I told you in the dynamic memory video and in the arrays video, we cannot make the size of an array dynamic because of multiple reasons that I already explained. Alright, so we can't do it here. So let's for now just quickly put them in here normally, so that we don't get an issue and that we can compile the code. Now, if we would try this out, let's maybe go back to the Solution Explorer. Yeah, we are still at a startup project. If I would try this out now, it should really make no change. Arrays equal before copy 0, after copy 1. And if I would go into there, you would basically see that nothing has changed. The code still works the same. And that's exactly what we have done. We have just replaced like this 32 with a count. However, this has one issue. First of all, if we are not making a mistake, it works. That's not a problem, but it has an issue. So what is the issue that we have? Well, the issue is that we are using count here always to read from it. So what could happen? Well, it could happen that we, for example, set count to a different value. So, for example, to a really big integer. If I would set this to a really big integer and try this out, well, we cannot do this. When we are doing memcopy, we are getting an issue that we are getting an access violation, reading, location, whatever. If I scroll a bit down, we get a few more informations here. But the point is, exception thrown at whatever in memory utils, access violation, reading, location. So basically, memcopy tries to read from array A and write to array B. Basically, the read to array A failed because we were reading at a location where we are not allowed to read because we had an issue. If that is quite low, if that value is quite low, like say for example 64, this is why I made this so high, it's actually working because we are currently on the stack. And the thing is, when you are on the stack, you have enough memory ahead that you can read and write without getting exception because it is the stack. However, you are doing unnecessary reads and writes, and that's not good. But if this value gets too big, we are kind of like going out of the range of the stack, and as soon as we are out of the range of the stack, we are getting this access violation. So basically the issue is that we can override that count, and that's not something that I want to do. I don't want to accidentally override that count here. That count should be at a constant value at all time. And actually we can tell C that this shall be constant. We can tell the compiler that the first time we are setting count, we're going to set it in a constant way so that it's no longer changeable. And that's what we're going to do here. And actually you can do this with every type imaginable. So the thing is, we have some modifiers that we can write to the type, which basically allow us to mark a a variable as a constant value, and thus only allow a once write, so that we can only write that variable once. And in this case we can do this basically by writing const before it. If I do this like that, like const in32t count, can see nothing changes here, all the same, we can assign it, but you can see that as soon as we have done that, it's no longer possible to assign a value here. You can see that the expression must be a modifiable L value, but count is a non-modifiable L value. So I cannot compile this, it's gonna fail. So it's no longer possible to override our count. And if I do this like that now, you can see it works again, and it's all looking good. So now you might think that since this is const, we can use it as a size for the array. So let's try this out. Can we use it? No, we can't. It's not possible to do this. In C++, there are ways around it. Something called const expression, but this is something that's not possible in C. In our case, it's not possible since that is still dynamic. This is still dynamic created, right? Count is still a variable that lives on the stack that can be in theory changed, corrupted. However, it's just not rewritable from our C language. So basically this is just a language construct. Const is just language construct, has nothing to do on how the code is actually generated. It will still not work here. We're gonna get to a way to make this a bit more dynamic in the future, but currently, well, we can just use it here. Now, actually, as you can see, we can use this even further. You can see that we are having the size computations where we are also always taking the size of and the count. So what I want to do here is as well is I want to factor this out. So I want to have another const in 32t size, which is going to be equal to count times size of in 32t. And now I can take the size wherever I had my computations, which is going to speed up our application because we don't need to recompute that value by sacrificing a few bytes on the stack, and also makes our code way more simpler to read and also easier to change. So now currently if I do this like that, okay, it works. And the only thing that I would need to change now if I want to make the array bigger is I would need to set this to 64, 64, and 64. And if I would start this now, well, works of course, but the array is double of the size. It's all working nice and automatically. It still shows you like this buffer overrun and a few things. This is just because Visual Studio is not really aware of what we are doing here. However, it does work. And as you can see, now changing the code is way more simpler. Well, of course, we really don't want to change this here at 3 times. Of course, if we would do this with malloc, we wouldn't need to do this. So basically what I'm going to do now is I'm going to simply do this with malloc. So I'm going to take that one and just write it in a malloc form. So malloc would be then the size, because we need to multiply this in. So if I would do this like that, we're just going to simply use malloc here. And when we are using malloc, of course, we need to verify that everything works. So if array A and array B, then we want to do our code. And down here, we want to free the memory. And if we have our array A, just going to inline this very quickly like that. I know that it's not the most cleanest way to do, but in this case it's reasonable, and I think more reasonable than doing it differently. So just to make sure that we can free the memory if it existed. Why am I doing this like that? Because I allocated them both here. And then I executed the code if they were valid, and so I need to check to deallocate or to free both if they ever existed. Alright, so this makes it quite easy. Let's start and see if it still works. Yep, still works. And if I would now want to change something, well, I could just go in here and change this to 64. And it works. Now we basically boiled this down to just one variable that we need to change. Of course, it is kind of bad because we are now going to the heap, and the heap is a bit slower than the stack. So if you would write a high-performant application, this is not a good idea. But that's why we also have C++, which is later on gonna make things like that way more easier with compile time code generation, const expressions, and amazing things that make our life way more easier. Alright, so now let's continue a bit more on that const here. So we use const above here to basically tell the compiler that we don't want to change count and size as the values. Now, in general, as you can see, we also don't want to change array A and array B, because when we copy the arrays, a naive programmer may say array B equals to array A, which you can see works because both are pointers. And now if I would basically assign array A to array B, I would basically completely discard the array B and have the array B also point to the data of array A. That's also the issue that I already explained, what you can do or make wrong when you're programming. And as you can see currently, we can do this. So as you can see, it is possible to assign these two to each other. And now you would think we can also handle this with const, right? Can we maybe say, all right, we're going to have a const int pointer and then basically do it like that so that we can't assign them? Well, actually, as you can see, it didn't really have the effect that we wanted. You can see that the copy is still possible. However, writing to our array A is not possible now. Basically what you're doing, if you are telling something that it is a cont int32t pointer, you're basically not setting the pointer to be constant, you're basically setting the values to which the pointer is pointing to constant. So basically this const int32t pointer doesn't mean a constant pointer to an array of int32t elements. This means a pointer to an array of constant int32t elements. So the elements are constant, but the pointer is not. So as you can see, by kind of like, this is the same that it is here. So basically the type is constant, not the pointer. And this is why we can still assign them. However, we cannot write to that array A above here. Memset is a different story. Memset actually automatically converts this pointer to a const pointer. If we would build it, it might fail on memset. As you can see, it doesn't fail. On C++ is a different story. On C++, this is going to fail. However, in C, it's just showing us a warning, and it's basically telling us that we have different const qualifiers, and different const qualifiers basically mean that the function expected a different type of pointer, or a different type of pointer than we have given it. So memset expects a non-const pointer, but we have a const pointer. The same here on memcopy. It's also yelling at us at the free function, which is something you would probably want to ignore because we don't care on the free function if the pointer is to constant elements. Actually, we really care, because if we are getting our memory with like that, like const int32t pointer, we are never going to modify the value that the operating system gave us. So actually the warning is okay at the free. So how can we solve this issue? Well, instead of basically telling that we want to have the type as constant, we basically tell that we want to have the pointer constant. And we can do this by writing the const after the type. So when we had it before the type, we were basically specifying that the type itself is constant. So a pointer to constant integer values. However, if we are doing it after the type, so now we have the type on the left, the type is a pointer to int32 values, and we have the const on the right, we are basically telling, all right, the array A shall be const and the array B shall be const, which is going to invert the behavior. We can now write to array A. However, as you can see, we cannot assign array A to array B, which is exactly what we want, because, well, they shall not be assigned to each other. And the other thing is, shall we ever modify array A and array B, the pointer itself? Is it a problem? Shall we ever modify array A or array B, the pointer itself? No, we shall never modify it, because we retrieve that pointer from the malloc function. And the malloc function returns us a pointer that the operating system has allocated for us. This pointer shall never be modified in our own code, because we get it from the operating system, and we need to preserve this pointer as long as we use it. And only after we call tree, we are kind of like allowed to modify it and to discard it. And that's why this is okay in this case. A different case might be if you're having a struct. If you're having a struct, and inside of the struct, you're having like an int32t pointer, data, well, which you might assign to null at some point. I cannot do this here, but if I would now like, let's maybe do this type def, let's do this properly, type def struct lol, So if I would have a lol here, then initially I might want to set that to null, which is kind of like a pointer to nothing. And later on I want to assign this to like a malloc call. I'm just gonna hard code this here. Then you might do some work on top of that, and then later on you might free x.data. And if you're freeing x.data, but the struct is kind of like still visible, or you are like having a function like void do work, function like that, where you kind of like take a lol pointer, lel, and then you basically say if not lel data, so if data is not existing, we are basically saying lel data equal malloc of 10, and then you are like doing some work, and on void consume something, where I also have a lol pointer, lel, where I like do maybe some work, and then after, or I would do this like that, if lel data, then do something, then I would do some work, and then I would free lel data. Then I also need to make sure that after I have freed it, to set this to a value that indicates that the pointer is invalid. So if you're doing it like that, you don't really want to have a const here. In fact, I think you might not even, yeah, I am actually able to do this in a struct, however, this is not a good idea, so if you're like storing something like that in a struct, you don't want to have this because you need to work with that maybe. So you need to assign it from a different function, and you might need to clear it from a different function, and you need to check if it's valid from a different function. So if you're doing it in a struct, you're not going to do it. However, if you're doing it like we have done it, like using it in the main function, we always want to make sure, or if we are doing it good practice, we want to make sure we make it an int pointer const variable so that we can't change it. So this is like what I would consider good practice, because this asserts that array A is never discarded. We don't lose the pointer here, because if we lose the pointer here, we can no longer free it, we run into issues. So that's what I would basically say as a good practice. And as you can see, the code is gonna still perform the same. And again, we are more strict, we are more clean, we have a bit better code here, and we learned the word const. And that's the idea. You can use const wherever you want. If you don't want to modify something, use a const pointer. If you don't want to modify the pointer itself, use a pointer const. Or if you don't want to modify the variable, use const in general. So in general, if you're doing the function, let's maybe quickly type the struct that again. Here, let's bring back the lel. I'm just gonna quickly put something in. So again, function do work. If you need to work or read the x value in here, but you don't need to modify it, then do it as a const lel pointer, lel. And if you need to modify it, like do setup, just use a lel pointer. You could also use here a lel pointer const. However, this is something that you really don't need, right? This const is not that big of an issue, because yeah, you might want to do this here as well, but it's not really like a big deal. You can also do this here. I actually can do this as well like that. You can do a const lel pointer const. So in this case, the data of lel is constant, and the pointer itself is also constant. So data constant, pointer constant. So you can really like mix and match them how you like them to make your things more constrainable and more safe. I can now also maybe go through a bit of the code that we used and make sure that we have this everywhere where we need it. Did we actually had it here? No, we didn't had it here in pointers, but I think it is simple C app. We had did we had a malloc call there? Yeah, like that malloc call. On that malloc call, you would want to make sure that you have the const here, for example, so that this is set it up correctly. Like you could also make all of these const. Not like that. Yeah, yes, like that. I don't know why I didn't want it. You could make these const, right? This works. However, it's not really required because they are copied. You don't modify like the original values. This is why I personally, if I create my own working copies for functions like as a parameter, I personally don't really want to put them constant here, so that they that's really pointless. It just makes the code a bit more complicated. And that's basically the idea, right? We now made this code also a bit more clean here. And the actual rest of the code is actually good. So now we learn const. I do want to quickly talk about another thing. We're just going to abuse our memory utils again for that. I want to talk about static. Static is a special keyword similar to const that you can assign to a variable. However, static has a whole different functionality. Static basically fixes a variable and makes sure that it is never like reinitialized. So if I would write a function that gives us a unique ID. So if I would write like a uint64t function get UUID, or not UUID, just get UID, unique ID. This is not a universal unique ID, it's just a unique ID. Unique ID means it is a unique identifier, so an identifier, a number as an identifier that is unique. In this case, it's unique because every call to that function gives you a unique identifier. On Windows, you probably know already UUID. UUID means universal unique, and universal unique means that you need to generate these and make these random and stuff like that, or not random, but have a special random number generator behind it that guarantees that the invocation of the same function on different systems to the same time on the same system to different times is not going to result in the same value. So for example, used on game engines, you're probably going to have UUIDs for each game object that you have in the scene, or each resource has a UUID. Basically, UUID, the idea is to identify your resources or anything in general. You call a function, get the UUID, and then you use it and assert that the ID was not existing previously. UUID works across multiple computers and across multiple launches of your applications. UID in this case just works on one system, on one launch of the application. So it's like a temporary ID. So how would we ideally generate such an ID? Well, the simplest way to do a unique ID is to start at the number 0, for example, and then count up every time somebody retrieves the UUID. So the general idea would be that you have like an ID here, which starts at 0, and here what you want to do is return ID++. So this now looks a bit interesting. What you would generally like expect me to do would be something like current ID, or let's keep my syntax here, current ID equals ID, and then something like ID++, and return current ID. Like this is the code that you currently understand, right? However, you can make this more readable and more easy to use, and we're going to use it quite a lot. We use ID++. What does ID++ means? ID++ is a so-called post increment. So basically what we are doing here is we are getting the ID, and after we kind of like got the ID, we're gonna increment it because the ++ is behind the ID. So this basically means return ID and increment it afterwards. So ID++ means take the old value and then increment. What you can also do is a so-called pre-increment, something like that, which is basically the other way around. Increment ID and then return it. In general, especially when we are getting to C++, this is more performant because this doesn't need to generate a working copy. This just increments the ID and returns it straight away. In terms of integers, it's really not a big deal what you're doing. If you're doing pre-increment or post-increment, doesn't make a difference. But in later on C++, we're going to see why it makes a difference, because we're going to implement both functions there. So ID++, give me the old ID, increment it. So we're going to start basically at 0. 0 is the first ID, and we are good to go. Now let's write a quick for loop here. So for u in 64 I equals 0, and let's say 64 IDs. And what I want to do here is I want to say my UID is equal to get UID, and then I want to do a printf, and I say UID is %I, and I'm going to do a sneaky \n that I'm going to explain to you in the next video, and I'm going to print the UID here. So what would happen if I do it? Do I have an issue? Yeah, because now we're having an issue. Like this I is for a normal integer. This I is for a so-called int32t, a normal int, assigned 32-bit integer. This is why we have that I think d would be double the size. Does that work? No, because it's unsigned. Can I do ud for unsigned double size? No, I cannot. These are a bit bitchy, these printfs. The percentage sign and then the parameters, they are a bit mad. They are going a bit mad if you're not using like default types like int, float, and all the things that are built in, like int, char, short. Like for these they are working very, very nicely. However, for these uint64t and uint32t, in general, we're having an issue because they can vary in size. But there are helpers that are gonna help us for printf here. So they are actually in another header. So they are in the header include int types.h. And if I would open up int types here, basically right click, go to document, you can basically take a look what is in here. And they are defining quite a few new functions in here. And they are outputting and they are defining the output format specifiers. So basically what you are wanting are these PRI macros. These PRI macros are basically specifying these specifiers. So you can like see this HHD, HDD, LLD, and all these are kind of like helping us to work with these integers. And you can see there are a hell a lot of these, and we are kind of like looking for U, because U should be unsigned, and we are using 64-bit. So we are kind of like looking for this pre-U64, which is LLU. You could remember these, of course, but I really would not recommend remembering these. So how would you write them in? You cannot do it like that, because if you're doing it like that, it's treating this as a string. However, what you can do is do it like this. This looks ugly and it doesn't make sense for you yet, but we're gonna get to it. We're gonna talk about this in the future, why this makes sense in the next video. And we're gonna talk about how this works and how all of this string stuff comes together. So if I would start this now, you can see that our code does not work. We are always getting a UID of 0. And why are we getting always a UID of 0? Well, it's very, very simple. We are every time if we call the functions getUID, the ID is going to be set to 0. So if we are calling the function the first time, okay, ID is created on the stack and it's set to 0. Now we are taking a copy of that ID, we are storing that 0 somewhere, we are incrementing it to 1, and we are returning the copy to 0. Next time we call into the function, ID is created on the stack, we are assigning it the value 0, we are storing a copy of the value 0, we are incrementing ID, and then we are returning the copy of 0. So you kind of like can see, since we are working on the stack, we always get a new copy of ID that is initialized to 0. However, what we can do is we can basically tell the compiler to not put this on the stack and to put this in a special location in our application. So our application has several sections into which the stuff is compiled. We have a section where our code is compiled, so all the instructions that need to be executed, they are in a section that is specially flagged to just be able to execute from there. So basically the code of ours have is stored somewhere. We have the stack that is stored somewhere. We have the heap that is assigned somewhere, and we have then several other text areas. So we have the default text area, which is the text area where also the code is stored. Inside of this text area, all of these values are like stored, like these string here, UID, double point percentage, \n, pre-U64, they are kind of like also stored somewhere with our code in a special section. And what we also have is a section that is also available once per application, but it is writable. So by default, our code is not writable. All of these strings, they are not writable, they are fixed. And what we basically do by specifying this ID in a certain way that we're going to see in a second, we could put it in a separate section where all so-called static data is put. And the static data basically means that it is data that is statically existing in the application. So it's a block of data that is statically there. You can read it, you can write it, you can do whatever you want from it, but it is statically there. You cannot like dynamically instantiate from this. It's a static instance. And static is also important if we are getting to C++, but in C it's even more important than in C++. So how would we now tell it to put this in the static location? Well, very simple. We're going to tell it that this is a static uint64t. And basically by putting this to static, we are basically moving away the initialization and the location. So by taking this to static, it's no longer stored on the stack. It's stored somewhere else in memory. It's loaded by the operating system. It's somewhere stored in our exe, and it is basically loaded. So basically we are kind of like generating a kind of like preset inside of our exe file that we are compiling, where we kind of like have all of our static data in there. For example, this ID, set it to 0. And now basically by using this like static, we are kind of like always writing to that ID value that is somewhere in the static section. So as you can see, basically, this is actually never being called. This looks like that if the code is compiled, because this is stored somewhere else. By static, we are saying it's stored somewhere else. It's not part of this function. So basically, we have moved the ID off to the static section and initialized it to 0. And if we try this out now, try it again, you can now see that now our UID assignment is working. So our first UID was 0, the second one was 1, the next one 2, the next one 3, and so on until we get our UID of 33. And that's all you need to know. So just put static before any variable that you want to do, and it's going to be always persist. Now, one thing that we now could try is to make another UID function. So we're gonna call this UID A and UID B. This is because I just want to make some observations here. So UID A and UID B. So UID A, UID B, and we're gonna see if this works. So now let's copy this as well here, that section. And let's do this with an ampersand and UID B here, UID A, UID B, and let's see what it does. And as you can see, it still works. You can have two UIDs. Just because they are named the same doesn't mean that they are the same. So it's not possible to create a static ID and use it everywhere. So it is kind of like bound to that function here. You could do this somewhere here. If you're doing it like here, where you would do this here, so let's do the ID here. If I would make this there, in the global application, so no longer in the function, globally in our C file, if I do it like that, surely enough, you can see that these IDs are no longer unique. We are starting at 2, then we are going to 3, 4, 5, 6, 7. Why did we start it by 2? I think this is actually an issue of our console, or is it of our code? Let's quickly rerun this. Yeah, it starts at 0. It was just an issue of the console. You can have weird issues with static variables, especially if you are using them extensively. If they are just in one function and you have an assertion that this function is never called, this always that the first call always finishes before the next call to that function comes, which only applies to multi-thread programming, but that's a whole different topic. If you can assert these, then it's always working. So one thing that I would never do is have a static variable like that in a global section. It's not something that you want to have. This is something that you want to treat with great respect. Really, really important. Great respect here. Never do this. You should never have something global. Like everything that is here is global, and everything that is global is not good, and that's what you want to avoid. Later on in C++, we're going to have some kind of global stuff, but you want to avoid global stuff. Just avoid it. It's better to avoid global things. So that's why I also didn't like really teach you how to do something global. So yeah, that's really the thing here. So just to wrap it up, you have learned two things today, two keywords for variables. You have learned const and static. Const allows you to make a variable constant so that the value can't be changed. For example, if you're writing it before the type or around the type, for example, const inserted to t or const inserted to t pointer, you are basically telling it that the data is constant. So in case it's a normal type, the int is not changeable. If it is a pointer, you can of course still change the pointer. However, you cannot change the content to where the pointer is pointing. If you are writing it the other way around, so after that type, so inserted to t pointer const, then the pointer itself is constant, but the data is not. So you can modify the data the pointer is pointing to, however, you cannot modify the pointer. These const things really help you to make your code more robust and more reliable against errors. Const is just a language construct. Const really is not changing how your code works. It is just helping you to not make mistakes by basically flagging, all right, I don't want to change that struct, so I'm going to make a const pointer. And if I would do a const pointer there, the function cannot change the contents and it can just read them. Or, well, the count is going to be constant. I'm not accidentally changing it during the execution of that function, or something like that down here. The pointer that we receive from malloc shall not be modified by having an inserted to t pointer const, so that we don't accidentally override it and then have issues with free or accessing it in our application. So a little nice helper. The story is a bit different for static. Static is actually doing some heavy work. Static is moving a variable away from the stack to the so-called static section. The static section is unique, so if you are defining a static variable in a function, you're always going to access the same value. If you change it with the function, it's going to persist. The change is going to persist because the changes are made in the static section, which is not reinitialized with the stack. And that's all for that video. I hope you enjoyed. Next video we're gonna talk about strings finally. We abused them today quite hard. You saw that \n, you saw like all this madness with these end of quotation marks and these pinky stuff in between there. But that's all something that we're gonna talk about in the next video. So thank you for watching. Make sure to like and subscribe and have a nice day. Bye.